Welcome back, everyone. In this video, we're going to continue our discussion of thermochemistry and focus on enthalpies of formation. In order to talk about the enthalpy of formation, we need to talk about standard state conditions, the standard states of the element. And by doing so, we can then use the standard enthalpies of formation, sometimes also called standard heats of formation, to find the enthalpy change for any reaction. So let's begin. What do we mean by the enthalpy of formation? So the standard enthalpy of formation is the heat that is given off or absorbed when elements combine to form 1 mole of a compound. The enthalpy values are measured at standard state. In other words, 1 atmosphere of pressure and 25 degrees Celsius. And each reactant, again, must be an element and must be in its most stable form under those conditions. The symbol naught denotes that we're talking about standard state. So this is a new symbol, and this is referring to the fact that we have a pressure of 1 atmosphere and 25 degrees Celsius. Note that the temperature here is different from standard temperature and pressure for gases, which was 1 atmosphere of pressure, but 0 degrees Celsius. So this reaction here is an example of the where the enthalpy of the reaction is equal to the standard enthalpy of formation. And the reason for this is because we're taking our substances, our elements, in their most stable form at 1 atmosphere of pressure and 25 degrees Celsius and converting them into 1 mole of a product. So as a recap, the enthalpy of any reaction is going to be equal to the enthalpy of formation when there's 1 mole of a single compound for our product and when the reactants are elements in their most stable state. So how could this not be equal to the enthalpy of formation? Well, if we were to double our reaction, now that's no longer the enthalpy of formation because we've produced 2 moles of a compound and not 1. That would be equal to twice the enthalpy of formation. Another way that we could modify this is if we take our elements and they are no longer in their standard states. So oxygen not as a gas, but as a liquid. So this would still have a value for the enthalpy of reaction because energy is still exchanged, but that value is not equal to the definition of the enthalpy of formation because at that point, the elements are not in their most stable state. For any element that's in its standard state, the enthalpy of formation is 0. Let's think about this. Let's say that we were to take oxygen in its standard state, and we form oxygen in its standard state. What's the energy change required for this to happen? Well, since I started and ended in the same state, there is no change. Therefore, for elements that are already in their standard states, the enthalpy of formation is defined as being 0. So again, another example here is looking at from carbon graphite to carbon graphite, the enthalpy of formation is 0. There's no energy required to do that because nothing actually changed. So what are the standard states? Again, we're talking about a temperature of 25 degrees Celsius and a pressure of 1 atmosphere. This is sometimes referred to as standard ambient temperature and pressure. Notice that the vast majority of the elements are solids. We have 2 elements that are liquid at room temperature and 1 atmosphere pressure. That would be bromine and mercury. And there are a handful of gases: hydrogen, nitrogen, oxygen, fluorine, chlorine, and then the noble gases. So you need to be familiar with the standard states of the elements. Additionally, you need to be able to distinguish between various allotropes. And an allotrope is an element in a different a different combination. So for example, oxygen versus ozone. These are allotropes. It's the same elements, but different ratios. And so oxygen in its gaseous form versus ozone in its gaseous form are different from each other. This is standard state for oxygen. This is not standard state. The ebook goes through and delineates other examples, but they include elements such as carbon, phosphorus, sulfur. These are some common elements that you need to be familiar with. What's the most standard state? All right, so let's do a practice problem here. For which one of the following reactions would the enthalpy of the reaction be equal to the enthalpy of formation? Pause the video and try and determine this on your own, and then I'll walk you through a solution. Welcome back. So, under what conditions does the enthalpy of reaction equal the enthalpy of formation? It is true when we form 1 mole of a single compound as a product, and then when the elements are in their most stable state in the reactants. So let's evaluate each one of them. A has an enthalpy of reaction, but it is not equal to the enthalpy of the standard enthalpy of formation. It's actually equal to 2 times the standard enthalpy of formation. If we were to divide everything by 2, then in that case, that would be equal to the standard enthalpy of formation. B is not the case. B is actually the reverse reaction. It's taking the compound and breaking it down into its elements, which are in their standard states. C is correct. We form 1 mole of product, and we use elements that are in their standard states. Oxygen is gaseous, and aluminum is solid in its standard states. For D, this one is similar to A. This is 2 times the value of the enthalpy of formation. And then E is not correct because oxygen has its standard state of O2, not O3. So now let's take a look at how we can use the standard heats of formation in order to calculate the enthalpy of reaction for any given chemical reaction. What we do is we take the enthalpies of formation for our products and our reactants, and we take the difference between them. We can use this only when our reactants and products are in their standard states. So in this equation, the enthalpy of the reaction, the standard enthalpy of the reaction, is equal to the sum of the standard enthalpies of formation of the products minus the sum of the standard enthalpies of formation of the reactants. And here we see N and M are just the stoichiometric coefficients of each product and each reactant respectively. This is an application of Hess's law. Remember, for Hess's law, it doesn't matter what path you take, as long as you start at A and you go to B, then the enthalpy of that reaction will be the same, regardless of if you go up to Z and then down to X and then back to G. So here's an example. How much energy would be produced in the thermite reaction that is listed there on the screen? You're given the enthalpies of formation of iron oxide and aluminum oxide. But we're not given the enthalpies of formation for iron and aluminum. The reason for that is because for elements that are in their standard states, the enthalpy of formation is 0. So if we want to find the enthalpy of reaction, we take the products, aluminum oxide, times its enthalpy of formation, plus 2 times that of iron, which is 0, and we subtract the enthalpy of formation of the aluminum and the enthalpy of formation of the iron oxide. Simplify, and you get negative 851.5 kilojoules. In the ebook, you can look at figure 16-4-3 to see this chemical reaction in action. It's really cool. I recommend that you do. All right, now here's an opportunity for you to practice. For this question, what is the standard enthalpy of reaction for the complete combustion of 1 mole of solid sucrose? The enthalpies of formation of sucrose, water, and carbon dioxide are provided for you. So I'd like for you to pause the video and try this one on your own. Welcome back. So what do you need to do here? You first need to write out a balanced chemical equation for the combustion of sucrose. You should have been able to predict that we would produce carbon dioxide and water using the sucrose and oxygen. You can then balance it one element at a time, starting with carbon or hydrogen and then oxygen. After we do this, now we take and we multiply the enthalpy, the standard enthalpies of formation for each substance times the coefficient of that substance in the balanced chemical equation. So that's going to be the sum of the enthalpies of formation of our products minus the sum of the enthalpies of formation of our reactants. Our products are carbon dioxide and water. So we take 12 carbon dioxide times its standard enthalpy of formation plus 11 water times its standard enthalpy of formation. And we subtract the standard enthalpy of formation of the sucrose. We also subtract the standard enthalpy of formation of oxygen, keeping in mind that because oxygen is an element in its standard state, that the standard enthalpy of formation is 0. We do the algebra to simplify, and we get our final answer of negative 5,644.1 kilojoules. That's it for this video. Thanks for watching. Have a great day.